3I Atlas is currently transporting a massive cluster of mysterious and unidentified objects, and scientists cannot fully explain what is happening. There is something riding through our solar system at this very moment. An interstellar visitor, one that arrived from the deep void between the stars, has developed a tail that points in entirely the wrong direction. It is not flowing backward away from the sun, as the laws of physics usually demand, but rather it is projecting forward, aiming straight into the solar wind like a sharp knife cutting against the current. That tail, which was seen glowing faintly in telescopic images captured just weeks ago, technically should not exist according to every single model we possess regarding how comets are supposed to behave. And yet, there it is, sharp and persistent, completely defying the rules. But here is where the situation becomes truly unsettling. A growing number of researchers now believe that this tail is not merely an optical trick or a strange quirk of dust geometry. They believe it is a swarm of unknown objects traveling ahead of the main body, bound together by gravity, and glowing from sunlight reflecting off solid surfaces that we cannot yet fully resolve. This object is 3I Atlas, the third confirmed interstellar object ever detected passing through our cosmic neighborhood. And it is actively rewriting the playbook on what we thought visitors from beyond could carry along with them. Imagine for a moment that you are staring at an image taken by one of the world's most powerful observatories. You see a bright nucleus, which is the comet's heart, and stretching away from it in the expected direction is a classic dust tail, faint and fuzzy, being blown back by solar radiation. But then, your eyes catch something else. You see another structure, one that is narrower and brighter, pushing forward into the sun, looking as sharp as a spear. Your brain stumbles because nothing in your experience of comets prepares you to see this. Every tail you have ever seen, and every educational diagram you have ever studied shows material streaming away from the sun, not toward it. And yet, this one refuses to cooperate. It sits there in the data, undeniable and reproducible across multiple observation runs, calling into question decades of settled science regarding how interstellar objects behave. Now, here is the question that keeps astronomers awake at night. What if that forward-pointing glow is not a tail at all? What if it is a cloud of separate objects, fragments, chunks, or maybe even intact bodies clustered together by the comet's weak gravity as it hurtles through space at tens of thousands of miles per hour? What if 3I Atlas is not traveling alone, but is dragging a retinue of unknowns along with it, a procession of material that predates its arrival in our solar system, possibly older than our sun itself? This is not science fiction. This is the hypothesis now circulating among leading astrophysicists. And it is based on observations you can verify yourself if you have access to the right telescopes and image processing software. The anti-tail of 3I Atlas, that is the term scientists use for this anomaly, has been imaged multiple times throughout late November and early December, and each new photograph deepens the mystery instead of resolving it. You have to understand how rare this situation is. Interstellar objects do not visit us often. We have confirmed exactly 3 in all of human history: Oumuamua in the year 2017, Borisov in the year 2019, and now 3I Atlas in late 2025. Each one has challenged our assumptions. Oumuamua tumbled through without any visible tail, sparking wild debates about whether it was a comet, an asteroid, or something for which we had no category. Borisov looked comfortably normal, a textbook comet with predictable outgassing and a well-behaved tail. But 3I Atlas is sitting somewhere between the two, exhibiting comet-like activity, jets of gas brightening near the sun, while simultaneously displaying this forward structure that has no business being there. And the timing couldn't be more critical. Right now, as you are hearing this, 3I Atlas is making its closest approach to Earth in its entire journey through our solar system. Observatories around the globe are training their instruments on it, collecting data at a pace we have never achieved with an interstellar visitor before. This is a live investigation unfolding in real time, and the swarm hypothesis is only gaining traction as more images come in. Let me paint the stakes clearly for you. If 3I Atlas is indeed carrying a swarm of objects, whether natural fragments or something else entirely, we are not just looking at a comet. We are looking at a delivery system from another star system, a capsule carrying samples of material forged under alien suns, tempered by radiation we will never experience on Earth, and now drifting within reach of our best instruments. Every chunk in that swarm, if it exists, is a messenger from deep time and deep space. Analyzing even one of them could teach us more about stellar evolution, planetary formation, and the diversity of cosmic environments than 100 theoretical models. But there is a darker edge to this excitement, one that responsible scientists are beginning to voice more openly. What if we do not know what we are looking at? What if our models are so tuned to objects born in our solar system that we are blind to the signatures of something genuinely foreign? We have had exactly 3 chances to study interstellar visitors up close, and each time we have been caught off guard by their behavior. Oumuamua showed non-gravitational acceleration without detected outgassing. Borisov showed unusual activity patterns. Now, 3I Atlas is glowing in the wrong direction. Pattern recognition is a survival instinct. And right now, that instinct is screaming that we are missing something fundamental about how matter behaves when it crosses the interstellar void. Stay with me here, because in the next stretch of this video, we are going to unpack exactly why leading experts are saying this interstellar guest might be carrying a swarm of unknown objects, what those objects could be, and why the answer matters far beyond astronomy. We are going to walk through the evidence step by step, weigh the competing explanations, and confront the uncomfortable possibility that our solar system is hosting something we do not have the language to describe yet. This is not hype. This is careful science meeting honest mystery, and you are going to see both sides of that conversation laid out in full. But before we dive into the deep analysis, I need you to do something for me. If this mystery chills you the way it does me, if the idea of a swarm of unknowns riding through our solar system makes your pulse quicken even slightly, hit that like button right now. Not for the algorithm, but as a signal. Every like on this video is a data point showing that people care about these questions, that there is an audience willing to engage seriously with cosmic mysteries without demanding easy answers. It tells observatories around the world that public interest in interstellar objects is real and sustained, which matters when research funding is allocated and telescope time is scheduled. And then drop a comment telling me where you are watching from, your city, your country, your corner of this planet. Because right now, as 3I Atlas streaks past Earth, we are all witnesses to the same event, separated by borders and time zones, but connected by the fact that something from beyond our solar system is close enough to study, and we are all asking the same question. What is it carrying? And why does it glow where it shouldn't? Your voice in the comments becomes part of the collective record of this moment, a timestamp of when humanity first seriously considered that interstellar visitors might not travel alone. So go ahead, like, comment, and then settle in, because what we are about to explore will change how you think about the space between stars and what might be drifting through it right now. Now, let us begin at the beginning with the facts everyone agrees on before we venture into the territory where scientists start disagreeing, because that is where the real story lives. The facts are simple, verifiable, and undisputed across every major observatory that has trained instruments on this object. 3I Atlas is an interstellar comet. Its trajectory proves it beyond any reasonable doubt. When astronomers plot its orbit backward, the math does not curve it around our sun in a neat ellipse like the comets we are used to. Instead, the path traces back out into deep space toward the galactic plane, implying an origin somewhere in the vast wilderness between stars. It is moving too fast to have been born here. The velocity and angle of approach are the signatures of something that fell into our solar system from outside, drawn by the sun's gravity, but not captured by it. It will pass through, swing around, and leave, never to return. That is what interstellar means in this context. A one-time visitor, a traveler passing through a neighborhood it does not belong to, observed only because we happen to be watching the right patch of sky at the right moment. The discovery itself came in the final months of the year 2025, when automated sky surveys flagged a new object moving against the background stars. Initial observations showed nothing extraordinary. A faint dot, possibly another asteroid or comet from the outer solar system, making an unremarkable trip sunward. But as more data accumulated, the orbit calculation started throwing up red flags. The eccentricity was too high. The velocity did not match anything gravitationally bound to the sun. Within days, the classification changed from routine to extraordinary. This was interstellar, the third confirmed object of its kind, and only the second with clear comet-like features. That confirmation triggered a global response. Observatories from Chile to Hawaii to South Africa began scheduling observation time. Amateur astronomers with advanced setups coordinated imaging campaigns. Space-based telescopes adjusted pointing schedules to capture this visitor during its brief window of visibility, and the data started pouring in. What the data revealed was an object behaving much like a standard comet in many respects. As 3I Atlas approached the sun, it began to brighten, not just from reflected sunlight, but from internal activity. Jets of gas and dust erupted from its surface as solar heat penetrated the icy nucleus, causing volatile materials to sublimate and vent into space. Spectroscopy confirmed the presence of water vapor, carbon monoxide, and other molecules we associate with comets born in our own solar system. The nucleus itself appeared to be several miles across, large enough to sustain this outgassing for weeks or months as it rounded the sun. A classic dust tail formed, stretching away from the sun in the expected direction, illuminated by sunlight scattering off microscopic particles blown free by radiation pressure. For a moment, it seemed like 3I Atlas would be the normal one, the interstellar visitor that finally fit our models without demanding revisions to textbooks. But that moment did not last. The anti-tail, first noted in late October imaging, became prominent post-perihelion, its closest point to the sun. Observers began noticing asymmetries in the brightness distribution around the nucleus. Some images showed what looked like a secondary structure, extending not away from the sun, but toward it. A faint spike of light that did not behave like the main dust tail. At first, this was dismissed as an artifact of image processing, a trick of stacking multiple exposures where slight alignment errors can create phantom features. But as independent observatories captured the same structure, dismissal gave way to curiosity. The spike was real, reproducible, and persistent across observation sessions separated by days. It was not noise. It was not a glitch. It was something physical, something attached to or associated with 3I Atlas, and it pointed in the wrong direction. By late November, as the comet made its closest approach to Earth, passing within a distance that allowed for unprecedented resolution, the strange forward glow became the dominant topic in the astronomical community. High-resolution images revealed that this anti-tail, as it was now being called, was not a diffuse haze, but a relatively sharp feature, narrow compared to the main dust tail, and significantly brighter than it had any right to be if it was simply an optical illusion caused by viewing angle. The geometry did not support the easy explanations. Anti-tails do appear occasionally on comets when Earth's position relative to the comet allows us to see edge-on through the comet's orbital plane, creating the illusion of a tail pointing sunward because we are looking through a dense sheet of dust from the side. But in the case of 3I Atlas, the math did not work out cleanly. The angle was wrong, the brightness was wrong, and the persistence across multiple observation nights was wrong. Something else was going on. And then the speculation began. At first, quietly, in private communications between researchers reviewing the data, and then more publicly as preprints started circulating and press inquiries came in. The anti-tail was not behaving like dust arranged in a favorable geometry. It looked more like discrete objects. Solid material, possibly clustered, reflecting sunlight more efficiently than gas-blown particles could. The sharpness suggested structure, not diffusion. The stability suggested gravitational coherence, not random dispersion. Observers started using words like swarm and cloud and cluster, terms that implied a collection of separate bodies rather than a continuous tail. And that is when the conversation shifted from documenting an anomaly to questioning what exactly was traveling with this comet from another star. Right now, as you hear this, 3I Atlas is moving away from the Sun and away from Earth, but it is still within range of our most powerful telescopes. The window for close observation is narrowing by the day. Every night that passes without capturing detailed images is a night of lost data, lost resolution, and lost opportunity to answer the most basic question. Is the anti-tail a trick of dust and light? Or is it a swarm of unknown objects gravitationally bound to the comet's nucleus? This is not a question we will resolve with theory alone. It demands data, high-resolution imaging, spectroscopy, and maybe even attempts to resolve individual objects within that forward glow if they exist. The urgency is real. The clock is ticking, and the astronomical community knows it. That is why observation campaigns are being coordinated around the clock. Why telescope time that was previously allocated to other projects is being reassigned. Why researchers are pulling late nights and sharing raw data in real time rather than waiting for peer review. Because if there is a swarm out there, and if we can study it before 3I Atlas disappears back into the interstellar dark, we will have learned something profound about what travels between stars and how such objects hold together across cosmic distances. But understanding why this matters, and why a swarm hypothesis is both scientifically plausible and deeply unsettling, requires us to first understand why that anti-tail should not exist in the first place. And that is where we turn next. Let us start with the basics of comet tails, because once you understand how they are supposed to work, the wrongness of 3I Atlas's forward glow will hit you immediately. Comets are dirty snowballs. That is the phrase astronomers love, though it is a bit reductive. They are chunks of ice mixed with rock and organic compounds, leftovers from the formation of planetary systems preserved in the deep freeze of the outer solar system, or interstellar space, for billions of years. When a comet swings close to a star, solar heat penetrates the surface, causing ice to vaporize. This outgassing carries dust particles with it, and both the gas and the dust form tails. But here is the critical part. Those tails always point away from the sun. Always. Not because the comet is moving backward, but because the sun's radiation and solar wind physically push the material away. Light exerts pressure. The solar wind, a stream of charged particles flowing outward from the sun at hundreds of miles per second, exerts even more. Gas molecules and tiny dust grains are light enough to be shoved directly away from the star, creating the spectacular tails we see in photos, sometimes stretching millions of miles into space. The tail does not follow the comet's motion. It follows the direction of the sun's push. This is first-year astronomy, textbook material observed in every comet we have ever studied. So when you see a tail pointing toward the sun, your brain should rebel. It is like watching water flow uphill. It violates the basic physics of radiation pressure and solar wind interaction. And yet, 3I Atlas has exactly that. A structure extending from its nucleus in the direction of the sun, bright enough to show up in multiple images, and stable enough to persist across observation sessions. The immediate question is, how? How does material defy the outward push and instead glow sunward? The first answer astronomers reach for is the anti-tail explanation, a known phenomenon that can create the illusion of a sunward tail under specific viewing conditions. Here is how it works. Comets shed dust continuously as they orbit, and that dust does not vanish instantly. It spreads out along the comet's orbital path, forming a thin sheet that extends both ahead of and behind the comet's current position. Usually, we view this from an angle where the dust sheet looks like a normal tail streaming away. But if Earth happens to cross the plane of the comet's orbit, or get very close to it, we end up looking edge-on through that dust sheet. From that perspective, the dust ahead of the comet becomes visible as a bright line pointing sunward, even though it is not actively being pushed in that direction. It is a line-of-sight effect, a trick of geometry, where we are seeing material that is actually moving away from us, but appears to point forward because we are looking through it sideways. This explanation works beautifully for many comets. In fact, several well-documented cases of anti-tails have been fully explained by this geometry. The problem is that 3I Atlas does not fit the pattern cleanly. Astronomers have run the numbers. They have calculated the orbital plane, plotted Earth's position relative to the comet throughout the observation period, and modeled how a dust sheet would appear from our vantage point. And while there is some alignment, enough to create a weak anti-tail effect, it is not enough to explain the brightness and sharpness of what is actually being observed. The forward structure is too prominent. It is not the faint, diffuse glow you would expect from scattered light through a thin dust sheet. It is a distinct, well-defined feature almost as bright as the main tail in some images that suggests something more substantial than a geometric illusion. It suggests actual material, concentrated and reflective, positioned ahead of the comet's nucleus in a way that resists easy explanation. Then there is the issue of persistence. Anti-tails from dust sheets tend to come and go as the viewing geometry changes. A few degrees of shift in Earth's position relative to the comet's orbit can make the effect vanish or reappear. But 3I Atlas's forward glow has remained visible throughout the entire observation window from mid-November through early December, even as the angles have changed. That consistency argues against a purely geometric effect. It suggests that whatever is creating that glow is physically there, moving with the comet, not just a fleeting alignment of viewpoint and dust. And that is when researchers started considering alternatives. What if the anti-tail is not dust at all? What if it is solid objects, fragments, chunks, maybe even intact smaller bodies traveling ahead of the comet, bound to it by gravity and reflecting sunlight off their surfaces. What if 3I Atlas is dragging a retinue of material with it? A cloud of unknowns that formed during its journey through interstellar space, or broke off from the main nucleus during a violent event earlier in the comet's history. This is where the swarm hypothesis begins to take shape. And it is not as far-fetched as it might sound. Comets do fragment. They break apart from thermal stress, from tidal forces when passing close to massive bodies, and from internal pressure as gases build up beneath the surface. When fragmentation happens, the pieces do not instantly disperse. They stay relatively close together, held by the weak gravity of the largest fragment and moving along nearly identical trajectories. Over time, some fragments drift apart, but others can remain clustered for years, even decades. If 3I Atlas underwent fragmentation at some point in its interstellar journey, perhaps during a close pass by another star, or from a collision with debris in the void, it could very well be traveling with a cloud of its own fragments. Those fragments, if they are large enough and reflective enough, would show up as a bright structure in telescopic images. And if they are positioned ahead of the nucleus due to slight differences in velocity or trajectory, they would create the exact appearance we are seeing, a forward-pointing glow that does not behave like gas or fine dust. But there is another layer to this, one that makes the situation even more intriguing. Observers have also noted jets on 3I Atlas, discrete plumes of gas and dust erupting from specific points on the nucleus. These jets are common on active comets. They are caused by localized venting as subsurface ices are exposed to sunlight. But jets also exert force like tiny rocket engines. And that force can push material in directions that do not align neatly with the sun's radiation pressure. If a jet is firing in the right direction, at the right intensity, it could, in theory, loft material forward ahead of the comet, where it might linger in a semi-stable configuration. Combine that with the possibility of pre-existing fragments, and you have a scenario where the forward glow is neither purely geometric nor purely new. It is a hybrid, a mix of ejected material and older debris, all clustered together in a way that amplifies the visual effect. The uncertainty here is genuine. No one is standing on solid ground with a definitive explanation. The data is ambiguous, the models are stretched, and the observations are too limited to resolve individual objects within the antitail, assuming they exist. What we have is a mystery anchored in real measurements. Brightness curves, spectral data, positional tracking, but open to multiple interpretations. And that is exactly the kind of situation where bold hypotheses emerge, where researchers willing to stick their necks out start proposing ideas that sound speculative but are grounded in the math and physics of what is being observed. One of those researchers is Avi Loeb, and his take on the 3I Atlas antitail is where the swarm hypothesis goes from intriguing possibility to headline-grabbing claim. Let us turn our attention there. Now, if you follow space, news with any regularity, you have heard the name Avi Loeb. He is a professor of astrophysics at Harvard, former chair of the university's astronomy department, and someone whose career has been marked by both prestigious contributions to theoretical astrophysics and a willingness to entertain ideas that make his colleagues deeply uncomfortable. He is the scientist who suggested that Oumuamua, the first confirmed interstellar object, might have been an alien probe, a claim that ignited fierce debate and positioned him as either a visionary willing to follow evidence wherever it leads, or a provocateur chasing headlines, depending on who you ask. Love him or dismiss him. Loeb has a track record of taking data seriously and proposing explanations that prioritize observational fit over conventional comfort. And now he has turned his attention to 3I Atlas and its anti-tail. And what he is proposing is both scientifically grounded and unsettling in its implications. In a recent essay released just days ago, Loeb laid out a hypothesis that cuts through the hand-wringing over dust geometry and viewing angles. He suggests that the anti-tail of 3I Atlas is not an illusion, not a trick of light, and not a sheet of scattered dust. Instead, he proposes that it is a swarm, a cluster of solid objects gravitationally bound to the comet's nucleus, traveling ahead of the main body in a relatively stable configuration. These objects, according to Loeb, are reflecting sunlight off their surfaces, creating the bright forward glow that telescopes are capturing. The key distinction in his model is that these are not gas molecules or microscopic dust grains being blown around by radiation pressure. They are substantial chunks, possibly fragments from the comet's own past fragmentation, possibly material that accreted onto the comet during its interstellar journey. Possibly something else entirely, but large enough and numerous enough to produce a coherent, observable structure. And because they are gravitationally bound, they move with the comet, maintaining their position ahead of the nucleus instead of dispersing into space the way loose dust would. Loeb's model hinges on a few critical points. First, he notes that the brightness and sharpness of the anti-tail are consistent with reflected sunlight off solid surfaces, not emission from gas or scattering from fine dust. Spectroscopic data, while limited, does not show the signatures you would expect from active outgassing in that region. There is no strong emission line from ionized gas, no clear evidence of sublimation. What you see is more consistent with passive reflection, light bouncing off solid material. Second, the stability of the structure suggests gravitational coherence. If the anti-tail were purely geometric, a line-of-sight effect through a dust sheet, it would fluctuate as the viewing angle changed. But it does not. It persists, which implies that the material creating it is physically there, moving in lockstep with the comet. Third, the position of the swarm ahead of the nucleus makes sense if you think about how fragmentation works. When a comet breaks apart, the fragments do not all move at exactly the same speed. Some get a slight velocity boost from outgassing or rotational forces. If those fragments end up moving slightly faster than the main nucleus, they will drift ahead over time, settling into a leading position from Earth. That would appear as a forward glow. Exactly what we are seeing now. Loeb is careful to label this as a hypothesis, not a proven fact. He acknowledges that the data is limited, that resolution is insufficient to confirm individual objects, and that alternative explanations have not been ruled out. But he also argues that the swarm model fits the observations better than the alternatives currently on the table, and that it deserves serious consideration and targeted follow-up observations. He is calling for high-resolution imaging campaigns, spectroscopic analysis of the anti-tail region, and even attempts to detect individual objects within the swarm if they are large enough to resolve. In other words, he is not just throwing out a wild idea and walking away. He is proposing a testable hypothesis and outlining the steps needed to confirm or refute it. That is how science is supposed to work, even when the hypothesis makes people uneasy. But here is where it gets more complicated. Loeb doesn't stop at suggesting the swarm is made of natural fragments. He opens the door carefully, cautiously, but unmistakably to the possibility that some of the objects in the swarm might not be natural at all. This is an interstellar object, something that has traveled for potentially millions of years through the galaxy, possibly passing near other star systems, possibly encountering environments and forces we cannot replicate or fully model. You cannot rule out the presence of material that has been shaped by processes we do not understand. He points to the precedent of Oumuamua, which exhibited acceleration that could not be explained by standard comet outgassing, and suggests that interstellar objects might carry surprises precisely because they have experienced conditions outside the narrow band of environments we have studied within our own solar system. It is a subtle argument, one that stops short of making extraordinary claims, but gestures in that direction. And it is this aspect of Loeb's work that draws both fascination and criticism. Critics argue that Loeb is too quick to jump to exotic explanations when simpler ones have not been exhausted. They point out that anti-tails are known phenomena, that dust geometry can be tricky, and that invoking swarms of unknown objects without direct evidence is premature. They worry that his high profile and willingness to engage with speculative ideas gives undue weight to hypotheses that should remain in the realm of interesting but unproven rather than being elevated to public discussion. And there is a fair point buried in that criticism. Science progresses through conservative steps, gather data, test simple models, add complexity only when necessary. Leaping to swarms and hinting at non-natural origins before exhausting natural explanations can muddy the waters and make it harder to separate signal from noise. But Loeb's defenders, and there are many, even among those who disagree with his specific claims, argue that his willingness to push boundaries is exactly what is needed when dealing with objects we have literally never encountered before. Interstellar visitors are, by definition, outside our experience. We have no direct data on how they form, how they weather, what they carry, or how they behave under stress across light years of travel. Every assumption we make is based on solar system objects, which might be a poor analog. In that context, entertaining bold hypotheses is not recklessness. It is intellectual honesty. It is an acknowledgement that we do not know what we do not know, and that sometimes the only way to make progress is to propose ideas that feel uncomfortable, and then design observations to test them rigorously. That is the approach Loeb is advocating for 3I Atlas, not blind acceptance of the swarm hypothesis, but serious, funded, sustained efforts to determine whether it is correct. And if it turns out he is wrong, that is fine. That is how science works. But if he is right, even partially, then we are looking at something genuinely new, and the implications ripple outward in ways we are only beginning to consider. One of those implications is the question of what exactly would fill such a swarm if it exists. What kinds of objects could survive the interstellar journey, cluster together gravitationally, and reflect sunlight in the way we are observing? That is not a trivial question, and the answers range from straightforward to deeply strange, which is where we need to go next. Imagine you are holding a handful of gravel. Now imagine that gravel has been traveling through the void between stars for 1,000,000 years, bombarded by cosmic rays, frozen to near absolute zero, exposed to radiation from distant suns, and never once touched by an atmosphere or a gravitational field strong enough to pull it together into a planet. What would that gravel look like? How would it behave? Would it still be recognizable as rock? Or would it have transformed into something stranger? Glass, crystal, fused metal, or organic compounds polymerized into forms we have never seen in a lab? That is the thought experiment at the heart of the swarm question. If 3I Atlas is carrying a cluster of objects, we need to ask not just how many or how large, but what they are made of and how they came to be traveling with the comet in the first place. The answers span a wide spectrum, from the comfortingly mundane to the genuinely unsettling. Let us start with the natural, straightforward explanations, because these are the ones most scientists default to, and for good reason. They do not require invoking new physics or exotic processes. The simplest scenario is that the swarm consists of fragments from the comet itself, pieces that broke off during a past event and have been traveling in close formation ever since. Comets fragment all the time. Thermal stress from repeated heating and cooling as they orbit stars can crack the nucleus. Tidal forces from close passes by massive objects can literally rip a comet apart. Internal pressure from sublimating gases can cause explosive outbursts that shatter sections of the surface. If 3I Atlas underwent any of these events during its interstellar journey, and it is plausible, given that it likely spent time in the vicinity of other stars before arriving here, it could easily have shed fragments that remained gravitationally bound. These fragments would be ice and rock, similar in composition to the main nucleus, ranging in size from boulders to small hills. They would reflect sunlight efficiently if their surfaces were relatively fresh and unweathered, which could explain the brightness of the antitail, and they would cluster ahead of the nucleus if they received even a slight velocity boost during the fragmentation event, settling into a leading position over time as gravity kept them from dispersing completely. This model is tidy. It requires no new assumptions about interstellar material or exotic processes. It is just standard comet physics applied to an object that happens to have an interstellar origin, and it fits a lot of the observational data. The brightness, the persistence, the rough geometry, all of it works if you assume a swarm of comet fragments reflecting sunlight. The main challenge is resolution. Telescopes on Earth, even the most powerful ones, cannot yet resolve individual objects within the antitail at the distance 3I Atlas traveled. We see a bright glow, not discrete points of light. So confirming the fragment hypothesis would require either much higher resolution imaging, possibly from space-based telescopes or future missions, or indirect evidence like spectroscopy, showing that the antitail region has the same composition as the nucleus, which would support the idea that it is made of the same material. But there is a second natural scenario that is less tidy and more intriguing. What if the swarm is not fragments from 3I Atlas, but material it picked up during its interstellar journey? Interstellar space is not empty. It is filled with gas, dust, and larger debris. Remnants of dead stars, particles ejected from planetary systems, and material that has been drifting for eons. A comet traveling through this environment at high speed would encounter some of this material. Most of it would collide and either stick to the surface or bounce off. But there is a possibility that larger chunks, maybe clumps of dust or small icy bodies, could be captured by the comet's gravity if the encounter happened at just the right velocity and angle. Over thousands or millions of years, a comet could accumulate a retinue of such objects, a collection of hitchhikers bound loosely by gravity and traveling in formation. This accreted material would not necessarily match the comet's original composition. It could be richer in metals if it formed near a different type of star. It could contain organic compounds or mineral structures we do not see in solar system objects. It could, in theory, be identifiable as foreign even if we cannot resolve individual pieces, because the spectroscopic signature would differ from the nucleus. This accretion scenario is speculative, but it is not wild speculation. We know that objects in space do capture material. Planets sweep up dust. Asteroids collide and stick together. The question is whether a small, fast-moving comet in interstellar space could accumulate enough material to create a visible swarm, and whether that material would stay bound over the timescales involved. The math is uncertain. Gravity weakens with distance, and a comet nucleus only a few miles across has incredibly weak gravity, barely enough to hold its own surface together, let alone capture and retain foreign objects. But it is not impossible, especially if the captured material is moving at very low relative velocity when the encounter happens. And if 3I Atlas did pick up hitchhikers, then the swarm we are seeing might be a sample of interstellar material from multiple sources. A composite object carrying pieces of different environments, different stars, different histories. That would make it scientifically invaluable. A mixed archive of the galaxy's material diversity delivered to our doorstep for study. Now, let us move into more speculative territory. The kind of ideas that make most scientists squirm, but that cannot be dismissed outright given how little we know about interstellar objects. What if some of the objects in the swarm are not fragments or accretions, but something else? Material that has been processed, shaped, or structured in ways we do not associate with natural comet behavior. I am not talking about alien spacecraft. I am talking about objects that might have undergone physical transformations during their journey that leave them looking unusual or behaving in unexpected ways. For example, prolonged exposure to cosmic rays and radiation can alter the surface chemistry of ice and rock, creating compounds and structures that do not form under normal solar system conditions. You could end up with surfaces that are unusually reflective, or that sublime at unexpected rates, or that have crystalline structures we would classify as anomalous if we saw them in a lab. These would not be artificial, but they would be strange natural objects shaped by unnatural, from our perspective, environments. There is also the question of density and composition. Interstellar space is mostly hydrogen and helium, but there are regions near star-forming clouds, near supernova remnants where heavier elements are more abundant. A comet passing through such a region could over time accumulate a coating of unusual material, metals, complex organics, even radioactive isotopes if it passed near a supernova. If fragments broke off later, they would carry that unusual coating with them. Viewed from Earth, such objects might have spectral signatures that do not match anything we have catalogued. They would be natural but exotic, and identifying them correctly would require rethinking our assumptions about what interstellar material looks like. This is not science fiction. This is the frontier of astrochemistry and planetary science. The recognition that the conditions out there between stars are vastly more varied than the narrow band of environments we experience in our solar system, and that objects shaped by those conditions might not fit our categories neatly. And then, because we are being honest about the full spectrum of possibilities, there is the whisper in the room that no one wants to say too loudly, but that keeps surfacing in comment sections, in fringe discussions, and in the more speculative corners of the scientific community. What if some of the objects in the swarm are not natural at all? What if they are manufactured, designed, intentionally placed? I want to be crystal clear here. There is zero direct evidence for this. None. No signals, no unusual materials, no structural anomalies that scream artificial. But the reason this idea keeps coming up is not pure fantasy. It is because Oumuamua set a precedent. When that object accelerated without visible outgassing, conventional explanations struggled. Loeb proposed that it might be a light sail, a thin reflective structure accelerated by radiation pressure, possibly of artificial origin. The idea was widely criticized, but it also could not be definitively ruled out because we did not have enough data. Now, we have another interstellar visitor exhibiting unusual behavior, and the same questions arise. If you are an advanced civilization looking to explore or sample other star systems, sending probes attached to comets would be a smart strategy. Comets are common. They travel between stars naturally, and they provide a gravitational anchor for lightweight probes or instruments. A swarm of small objects traveling with a comet would be easy to miss unless you were looking closely. And if you were looking closely, you might dismiss it as natural fragmentation unless you could get close enough to resolve details. Again, no evidence supports this. It is pure speculation, the kind of thing that belongs in the interesting to think about but not actionable category. But it is not crazy. It is a logical extension of the idea that other civilizations might exist and might explore using methods we would find clever if we thought of them ourselves. And the reason it is worth mentioning at all is that it frames the stakes. If the swarm is natural fragments or accretions, that is scientifically valuable, but not paradigm-shifting. If it is exotic material shaped by rare interstellar processes, that is more interesting, potentially opening new avenues of research. But if even one object in that swarm turned out to be artificial, even if it is just a simple probe or sensor, that changes everything. That means we are not alone, that we are being watched, or at least sampled, and that the galaxy is far more active and interconnected than we imagined. It is an infinitesimally small probability, but it is not zero. And that non-zero status is enough to keep the question alive in the minds of researchers and enthusiasts alike. So, what could fill this swarm? The most likely answer is natural fragments, ordinary comet debris, gravitationally bound and reflecting sunlight. The next most likely is accreted material, hitchhikers picked up during the interstellar journey. Further down the probability ladder are exotic natural objects shaped by rare processes. And at the very bottom, but still present, is the artificial hypothesis. All of these are on the table because the data does not yet allow us to rule any of them out definitively. And that ambiguity is precisely why the swarm hypothesis, whether you buy into it or not, is driving so much attention right now. It is a mystery with multiple solutions, and the only way to narrow them down is through better observations, more data, and rigorous analysis. But not everyone agrees that the swarm hypothesis is even necessary, and that is where the scientific debate gets sharp. Science thrives on disagreement. It is not a weakness, it is the engine of progress. When a bold hypothesis like Loeb's swarm model hits the community, the response is not universal acceptance or rejection. It is a clash of interpretations, methods, and standards of evidence. And right now, the pushback against the swarm hypothesis for 3I Atlas is vigorous, detailed, and worth taking seriously because it exposes the gaps in our current understanding and forces everyone to sharpen their arguments. The skeptics are not dismissing the mystery. They are questioning whether we need to invoke a swarm at all to explain what we are seeing, or whether more conventional mechanisms can do the job if we apply them carefully. This is the scientific method in action. Propose, challenge, test, refine. And the challenges being raised are not trivial. The first line of criticism focuses on the geometry explanation. The idea that the anti-tail is a line of sight effect through a dust sheet rather than a cluster of discrete objects. Critics of the swarm hypothesis argue that while the viewing angle for 3I Atlas is not perfect for producing a classic anti-tail, it is close enough that with some adjustments to the dust model, accounting for variations in dust size distribution, density gradients, and the specific timing of dust ejection events. You can reproduce the observed brightness and sharpness without invoking a swarm. They point to detailed simulations of comet dust behavior that show how even a thin sheet of dust, if viewed edge-on, can produce sharp, bright features that look nothing like the diffuse glow most people associate with tails. The key variable in these simulations is the size of the dust particles. Larger grains, pebbles, and small rocks, not just microscopic dust, are less affected by radiation pressure and settle into tighter, more stable configurations along the comet's orbit. If 3I Atlas has been shedding larger particles at a higher rate than typical comets, those particles would create a denser, brighter dust sheet that could easily explain the anti-tail without requiring gravitationally bound fragments. This is a powerful counterargument because it does not require new assumptions. It is just standard comet physics applied more carefully, and it has precedent. Several comets with prominent anti-tails have been fully explained by dust geometry once the models were refined to match the specific characteristics of the comet and the viewing conditions. The challenge for the swarm hypothesis is to demonstrate that the geometry explanation, even when optimized, still falls short. That there is something in the data that cannot be explained by dust alone. So far, that definitive proof has not materialized. The brightness is suggestive, the sharpness is intriguing, but neither is conclusive. And that leaves room for skeptics to argue that the swarm model is premature. A leap to complexity when simplicity might still work. The second line of criticism targets the stability argument. Loeb's model suggests that the swarm is gravitationally bound, held together by the comet's weak gravity as it travels. But several researchers have run the numbers on this, and they are skeptical. The gravitational pull of a comet nucleus a few miles across is incredibly weak. Far weaker than the perturbations caused by solar radiation pressure, the solar wind, and even the comet's own outgassing jets. For fragments to remain clustered ahead of the nucleus over weeks or months, they would need to be moving at almost exactly the same velocity as the nucleus, and they would need to avoid being pushed apart by all the forces acting on them. That is a delicate balance, and it is not clear that it is stable over the timescales involved. Simulations of comet fragmentation show that while fragments do stay together initially, they tend to drift apart over time, dispersed by even small velocity differences and external forces. The fact that 3I Atlas's anti-tail has remained stable throughout the observation period is seen by some as evidence against a swarm, not for it. Because a true swarm should show signs of dispersion, brightening or fading, spreading or concentrating as the fragments move relative to each other and relative to Earth. The lack of such changes suggests a more static structure, which fits better with a geometric dust effect than with a dynamic collection of objects. Then there is the spectroscopic critique. If the anti-tail is made of solid fragments, those fragments should have a spectral signature distinct from fine dust. Solid objects reflect sunlight differently than clouds of tiny particles. The reflection is more directional. The color distribution is different. And there should be detectable differences in how polarized the light is. Several observatories have attempted spectroscopic measurements of the anti-tail region. And while the data is noisy and limited, the preliminary results do not show strong evidence for solid body reflection. The light looks more consistent with scattered sunlight from dust, not mirrored reflection from rocky or icy surfaces. That does not rule out a swarm. Solid fragments covered in dust would look dusty, but it weakens the case. If the swarm exists, it is not revealing itself in the ways we would expect, based on how solid objects behave in space. There is also a meta-criticism directed more at the messenger than the message. And while it is uncomfortable, it is part of the conversation. Avi has a reputation for pushing speculative ideas,